Have you ever wondered what truly drives the movement of water, especially beneath the Earth's surface, making it flow uphill in some cases or staying put in others? It is a fascinating question that hydrologists and water scientists grapple with every day, and the answer lies in understanding the energy of water. At its core, elevation head and pressure head are distinct components of the total energy of water at a given point, known as hydraulic head. Elevation head represents the potential energy due to the height of the water above a chosen reference plane, while pressure head represents the energy due to the pressure exerted by the water. Think of elevation head as purely about vertical position, and pressure head as purely about the force pushing on the water. The fundamental difference stems from the forces they measure. Elevation head, often symbolized as the letter Z, is simply a measure of the vertical distance from a datum or a reference point to the water level. It is governed by gravity, meaning water at a higher elevation has greater potential energy simply because it can fall further. Pressure head, on the other hand, symbolized as P over gamma, where P is pressure and gamma is the specific weight of water, measures the energy contained within the water due to hydrostatic pressure, or the force per unit area. This pressure can be from the weight of the water column above a point, or from external forces acting on a confined aquifer, for example. Understanding both is critical because water always flows from areas of higher total hydraulic head to lower total hydraulic head, not just from higher elevation. To practically assess these, you might imagine a well or piezometer. The elevation head for a point at the bottom of the well would be its depth relative to a sea level datum. The pressure head at that same point would be the height of the water column standing in the well above that point. In an unconfined aquifer, where the water table is open to the atmosphere, the pressure head at the water table itself is considered zero, and the elevation head is equivalent to the water table elevation. In a confined aquifer, however, the pressure can be much higher than atmospheric, causing water to rise significantly above the top of the aquifer in a well, indicating a substantial pressure head. These concepts form the backbone of understanding groundwater movement through porous media, famously described by Darcy's law. When combined, elevation head and pressure head give us the total hydraulic head, which allows us to calculate the hydraulic gradient, the driving force for water flow. This gradient dictates the direction and rate at which groundwater moves, influencing everything from contaminant transport to the sustainable yield of water wells. It is a powerful tool for predicting water behavior. Grasping the individual roles of elevation head and pressure head is essential for anyone delving into water science. It moves beyond simply observing water's location and instead offers a comprehensive energy-based understanding of its dynamic behavior. By distinguishing between the potential energy of position and the energy of applied force, you gain a clearer picture of why water flows the way it does, enabling better management and protection of our vital water resources.
If you love learning about water, like, subscribe, and keep exploring with us.